So we want our y values, right? As opposed to our x values. So it would be f of c plus 1. And then it's rate of change, right? So we want the change. So that's the change in our y values. And then what are we basing that on? The percent change. So like if you leave a 20% tip when you go out to eat, what do you base that 20% on? Yeah, your bill before tip, right? So the initial cost of your meal. So f of c is our base. So it's, some people write like final value minus initial value over initial value. Right, so those two numbers are always the same, that f of c and f of c. Notice that these are all y values. The x value itself doesn't show up anywhere in the formula. So the numerators are the same for the average rate of change and the percent rate of change. What differs is that the average rate of change compares it to how much x is changing, whereas the percent rate of change compares it to what we started with. So what the initial y value was. Okay, so let's look at a table. When you have a table of values, you can determine if the function models a linear situation or an exponential situation just by calculating that average rate of change and percent rate of change and seeing which one is constant. We'll do the change in our y values. Divided by the change in our x values. Which is 1.3. And then to find our percent rate of change, again, the numerator is always the same. It's the change in our y values. But then instead of dividing by the change in your x value, you're dividing by your initial y value. So in lieu of anything else, you can always just copy that second number, which gives us 1.3 over 5, which is 0.26. So how would I find the average rate of change between x equals 1 and x equals 2? Mm-hmm. So change in my output minus, or divided by change in my input, gives me 1.3 over 1, which is 1.3. And then what about my percent rate of change? Mm-hmm. So change in our y value divided by that initial y value gives me 1.3 over 6.3. That one's not quite as easy to do in my head, so you guys are going to help me out. Let's say 0.206. So we can already see which one's constant. Theoretically, I mean, it could be that neither is constant. But You won't find that both are ever. So either you have a constant average rate of change, you have a constant percent rate of change, or you don't have either and the function just does something wacky. But if your average rate of change is constant, then your percent rate of change can't be constant unless it's a constant function, in which case it's kind of boring because everything's zero. Like all the change is zero. So you guys go ahead and do that last line. So find the average rate of change and the percent rate of change between those last 2 points. I have a couple things to get back to you. So we can write an equation for this function, and I would, if I were you, just try mostly to think about like how to build the equation as opposed to like memorizing a formula. Remember the other day when we did this, sorry, that's a loud vibration. When we did this, you guys didn't start with like mx plus b. You just kind of like wrote down what was happening, right? And so you can always do that, right? We start with our initial value, which is what? What's the value of my function at the very beginning? So that's the value of my input. Yep, so we want the initial value of the function, which is 5. And then are we adding repeatedly or multiplying repeatedly? So plus, and we are adding 1.3 repeatedly, so x times. So I like to do a little bit of a review of linear functions just so we can compare. But we'll spend most of the week on exponential functions. Is everybody cool with this one? Yes?
Exponential functions are always fractions, right? Or like they're always a percent. Like you're getting like multiplied by. Like if it's ever exponential. Like I noticed on my math lab.
Sort of.
The question ever asked if it was ever a percentage, like, or I mean, it always was exponential.
If there was a percent involved?
Yeah.
Yeah, typically if you have percent change, then it's always going to be exponential because it's a constant percent rate of change, right, is what defines exponential. There are plenty of exponential functions where it's not thought of in terms of a percentage, which we'll look at one in a minute. So we'll get to see one. But yeah, if there's a percent in the problem, then almost always it's exponential. So I have just a handout for you so you can keep this in your notes. So let's start with exponential growth. Again, just like we just talked about with that linear function, we can kind of just think about what's happening here, right? We start with some initial value, and then what operation are we doing repeatedly?
Multiply.
Yeah, we do multiplication, and we multiply by x factors of a. What makes this an exponential growth function as opposed to an exponential decay function is that the number that we're multiplying by repeatedly makes the value bigger. So it has to be greater than 1. Because if you multiply by a number less than 1, then that'll make it smaller. The variable is our exponent. And that's an important distinction because remember when we talked about, we had functions like this a couple weeks ago. As opposed to a function like this. So that first one is a power function, which is what all our polynomial functions are based on, right? Notice the variable there is our base, so it's saying what we're multiplying by repeatedly. So if I have like x equals 2, that's 3 factors of 2, and if I have x equals 4, that's 3 factors of 4. As opposed to an exponential function, what your input is the number of factors you have. And so if I put x equals 2 in, I have 2 factors of 3. And if I put x equals 4 in, I have 4 factors of 3. So my exponent is the variable here. What I'm multiplying by is constant. And so that distinction is important because, of course, they behave differently if it's exponential or a power function. So I always just remember that in an exponential function, like x is your exponent. So your input is your exponent. And in general models, so a lot of what we're going to be doing with these guys is modeling applications, so real life scenarios. And a large percentage of the time in those applications, the input is time. So in percent change problems, we're often talking about something changing over time. And so the exponent represents the time period associated with the change. It's always important to ask yourself what that input represents so that you're plugging the right numbers in, right? So when I say associated with the change, I mean that if somebody tells me that my bank account is going to increase 10% every month, and then they say, how much money do you have after 3 weeks? I can't put 3 in for x because x has to be the number of months because 1 month is associated with the change that was described to me. They said 10% each month. If I put 3 in for x, I'm finding the change for 3 months, not for 3 weeks, right? So whatever that percentage is or factor is has to be associated with the time period that you're using for x. The base A is the growth factor. So that's the number that we're multiplying by repeatedly. Sorry, this line is really short. So f of x is multiplied by when x increases by 1. So again, that x value or input is associated with the change described by that growth factor. So every time I increase x by 1, we're multiplying by a one more time. The coefficient of c is the value of f when x is equal to 0. Because what's a to the 0, no matter what a is?
1.
It's 1, right? So if I plug in 0, I get c times 1. So I'll always end up with c. So my y-intercept is 0, c. And this is growth. So today we're mainly talking about just models, so I'm not considering when x is less than 0 at this point. Tomorrow we'll look at it a little more theoretically, and we'll look at like the entire graph of these functions. So we increase at an increasing rate. Remember, that's what we figured out about exponential relationships, is exponential growth is growing, but it's growing faster and faster and faster and faster. Our percent growth rate is, we already said, the change in x value, or sorry, in y values divided by the initial y value. And probably more importantly than that, it satisfies the relationship A equals 1 plus R. So again, so if monthly my bank account is increasing by 10%, if I started with $500, is that how much money I have in my bank account after a month? It's not, right? That's what was added on. So in this situation, R is equal to 0.1. That's my percent growth rate. But when we actually get down to doing the multiplication, I have to factor in the 100% I started with, and then I want 10% on top of that. And so my actual growth factor is 1.1. So the 1 is the initial value you started with, and we always have to multiply by that to keep what we started with. And then whatever our growth rate is, we're adding on to that. And so we're multiplying by 1 plus R to get our growth factor. I think that that's probably the trickiest part of these, is just distinguishing between the percent growth rate and the percent growth factor. So I always just remember that the factor, the thing I'm multiplying by, includes what I started with. So 100% of what I started with, and then either plus or minus the change. Questions? Okay, let's look at decay. When it comes down to it, an exponential decay function is basically exactly the same as an exponential growth function. It just happens to be going down instead of up. So the structure and setup of it is essentially the same. Just like when we write the equation for a linear function, if it's got a negative slope or a positive slope, it doesn't really change how the equation is set up. So it's kind of the same idea here. Our equation is still c times a to the x. But what makes it a decay function is that a is a number that we would multiply by to make our output smaller. So it's between 0 and 1. Your growth or decay factor is never negative. Because imagine if the base of that was negative, and every time we raise it to an even power, we get a positive, and every time we raise it to an odd power, we get a negative, and so our y values would fluctuate between negative and positive, which is fine. I mean, there's functions that look like that, but they don't behave exponentially. So our base is always positive. What makes this decay is that we're multiplying by a number less than 1, so it's like we're taking a third of something and then a third of that and a third of that, which makes it smaller and smaller and smaller. Again, all of this is the same. My variable is the exponent, which again corresponds to the time period associated with the change. My base is the decay factor. Which is the value at f of x, by which f of x is multiplied every time x increases by 1. Regardless of what a is, raising it to the 0 power always gives me 1. So that c is always our initial value, corresponding to an x value of 0. So my y-intercept is the same. So see, everything represents the same thing. It's the only thing that differs here is what that value of a is. That's the only thing that makes it decay rather than grow. So with decay, we're starting up here, and then we're decreasing. And with exponential decay, we decrease at a decreasing rate. So whereas exponential growth gets steeper and steeper and steeper, exponential decay gets shallower and shallower. It kind of levels off. Will my output ever be 0? It won't, right? Because the only way to get 0 through multiplication is to... And so no matter how small it gets, it's never actually going to hit 0. It'll get smaller and smaller and smaller. So we approach 0. So we have a horizontal asymptote at y equals 0. We'll get infinitely close to it as x gets bigger, but we're not actually going to have an x-intercept. And then our percent decay rate, again, is exactly the same. So the change in our y values over the initial y value. The difference here is that this number is going to be negative. Right, because if I have 2 points and I subtract the rightmost y value minus the leftmost y value, that's always going to give me a negative if it's going down to the right. And so our percent decay rate is always negative. And it still satisfies exactly the same relationship between that decay factor and the percent decay rate. So I usually, in terms of decay, I usually think of this as like what is being lost. Whereas my decay factor is like what's left. So if the value of my car decreases by 10% every month, then my percent decay rate is negative 0.1. That's what I'm losing every month. But my decay factor is 0.9. That's because my function would calculate the value of the car. And so we want to find what's left after each month. We don't want to find what we lost after each month. So I take the 100% value that I started with, take away what I'm losing, and that leaves me with the 90% that's left. And so that's my decay factor. That's what you're multiplying by, is what's left of the 100%, not the part that you're losing. Questions? Okay, let's talk half-life. So you guys have heard of carbon dating, yeah? So the way they do carbon dating is they look at the half-life of a substance, which is basically the rate at which it decays, figure out how much is left of something, and then they can figure out how long it's been sitting there. So the half-life of a substance is how long it takes for it to decay by half, so lose half of its mass. In this case, they say the half-life of a substance is 200 years. We're starting with 100 grams. That means after 200 years, 50 grams will be left. So we lose half of what we started with in 200 years. Notice that X is the number of half-lives. It is not the number of years. Because we lose half the substance every half-life, not every year, right? That X value has to be the time period associated with the change. So the change that's occurring is that we're decaying by half. The time period associated with that is 200 years, or one half-life. So in order to write a function, the first thing we'll do it just for the heck of it. The first thing we ask is it linear or exponential? Which is it? It's exponential, right? Because the amount of the substance that I lose each 200 years is based on how much I had, right? It's not the same every 200 years. It's based on what I had in the period before that. And so I'm losing a fraction of it every 200 years. not a set amount. Because, I mean, if I lost 50 grams every 200 years, then after 400 years, it'd all be gone. Yeah. So it's exponential. And then I want to know if it is growth or decay. This may seem like a silly question because it's often pretty obvious, but you want to be really aware of exactly which it is, because our value, our percent change, is negative for decay and it's positive for growth. So if we don't think carefully about which one it is, then it's easy to get the sign of your fact or your percent change incorrect, and then that messes with all the numbers. So is this one growth or decay? Yeah. Decay. So we're losing the substance, which means we have a negative R. So next we want our percent decay rate. So the percent decay rate is what we're losing. So what do we lose every 200 years? What percentage of our substance?
50%.
Right, half of our substance, or 50%. So R is equal to negative 0.5. Every 200 years, we lose 50%. In half-life problems, it is always 0.5. So the thing, it's kind of tricky because in a lot of problems that we do, that percentage changes, whereas in half-life problems, the period of time changes, and it's always 50%. So when we talk half-life, we're always talking about how long it takes to lose 50%. So that percent rate of change, or percent decay, is always 50%. And then what varies is how long it takes to lose the 50%. So we can't write a function with just R, right? What actually goes in our function is what we're multiplying by repeatedly, and that's our decay factor. So decay factor what's that going to be? How's that related to the decay rate? Sort of, in this case.
Next part. It's just 50 number of cycles.
It's just half of whatever the amount left is.
How is the decay factor related to the decay rate?
Determines the
It's how many half-lives there are, right? Are they the same in this problem?
Look at your... So what I'm trying to get you to do is look at your piece of paper so that when you do your homework, you'll look at the piece of paper. How is the decay factor related to the decay rate?
Well, the decay rate is what's being lost.
Mm-hmm.
And the decay factor is what's left.
Mm-hmm. Which I can find how. It is the last thing on both sides of that piece of paper.
What's the identification?
Yeah. It's the 100% I started with plus my rate of change, my percent rate of change. So in this case, it is 1. So I start with 100% of the substance, and then I lose half of it. Whoops, I forgot my negative. So I am left with half of it. I lose half, I'm left with half. The fact that those are both 0.5 is simply a result of the fact that our rate of change is like half. That's not like a generalization that you can make that they're the same. It's because if you lose half, you're left with half. If you lose 70%, you're not left with 70%, right? They're not always the same. It's just because it's half and half. What's our initial value?
1.
So the function I'm writing tells me the amount of the substance that I have. So the initial value should be the initial amount of the substance, which is 100 grams. So my function f of x equals, well, you should always start with what you started with. So we started with 100 grams. We are repeatedly halving it. So every half-life, we reduce by a half. So we're left with half. If you write down all this stuff, then you guys have a formula on that piece of paper that tells you how to get it, your function, every time. How much is left after 400 years? Well, there'd be 50 grams after 200 years, right?
Oh, yeah.
25.
So f of something is 25 grams. F of what? Good. So when x is 2, my output is 25 grams. We got that 25 grams just by having it twice, right? Just because it's pretty simple to say 400 is just 2 half-lives. But in general, the number of half-lives which is our x value, is the number of years divided by whatever the half-life is. That's important because if you put 400 in for x, you'll get a very, very different result than putting 2 in for x, right? We always need to remember that our input represents the time period associated with that 50% loss or whatever the percent change is. And so we can't always just like throw in whatever number. We have to think about converting it into those time periods. So in this case, we had 400 years divided by a 200-year half-life. That's how we got the 2 that we plugged in. So try this one. How much is left after 1,065 years? So what would we do there? Mm-hmm.
1,065 by 200.
Mm-hmm. So first we need to figure out how many half-lives have passed after 1,065 years. And it is 325. So that's our x value. What should I do with that?
Plug it into a function.
Yeah, then we just plug that into our function, right? The amount of substance that's left, whoops, after 5.325 years is equal to 100 times 0.5 to the 5.325, which gives me what?
2.494.
So about 2.5 grams. Very good. I will tell you that this model is totally unrealistic, because the fact that we use that 0.5 is really saying that, like, I have 100 grams for the first 199.99999999999 years, and then poof, when 200 years hits, like 50% of it goes away, which is not realistic at all, right? We know that it gradually declines. In order to model that, we need a continuous exponential decay model, which we'll do later in the week. But these ones, although somewhat unrealistic, are nice because you can see where that percent change like fits into the whole model, whereas it's a little harder with the continuous models to see like where all the things we know about the situation actually fit into the function. So we'll do those later to see more realistic models, but for now we have to kind of think of it as like a every month, every year, every week type thing rather than a continuous change. Real quick, let's talk about bunnies. Is this linear or exponential? It is exponential. Is it growth or decay?
Growth.
Good. Where this gets interesting is when we talk about the growth factor. I don't know how to spell growth, apparently. There we go. And the percent growth rate. Do we know either of those? I mean, technically we know both of them, but in the problem, what do they give us?
Growth factor is 2 times 3 units.
Right, so because the no wait, it's not 2. The growth so remember the growth factor is the number we multiply by, right?
Isn't it a to 3 to the x? Or a times 3x?
So the growth factor isn't the function. It's just the factor that we multiply by repeatedly, which is what?
Just 3.
It's 3, right? I mean, if it triples, how do you triple 2? You multiply by 3, right? And then you triple that by multiplying by 3 again.
Yeah.
What's the percent growth rate? If you start with 100% of your bunnies and you triple it, so if it was 300% and you started with 2, you would be adding 6 more bunnies and you'd end up with 8 bunnies. So you'd go from 2 bunnies to 8 bunnies. Is that what's happening? What are you actually adding on to that 100%?
3. Hold on.
So you start with 2 bunnies. Does everybody agree with me that after a month you'll have 6 bunnies?
Yes.
Okay. So we know that that is times 3, which is 100% of my bunnies plus what percent of my bunnies that I started with? 200%. The increase is 200%, right? I haven't increased the number of bunnies by 300% because I started with 100%. The way that you end up with 300% of the bunnies you started with is by increasing it by 200%. It's a little bit weird when you get percentages over 100. Like, it makes perfect sense when we're like, oh, if I leave a 20% tip, I'm paying 120% of my bill. It feels a little bit weird when the percentages get over 100. But remember that relationship between the growth factor and the growth rate is always that the growth factor is 1 plus the growth rate. So here my growth rate is 2. Be really careful when you're writing functions if they're giving you the percent change or if they're actually giving you the number that you multiply by to get the next value. So here they gave us the number that we have to multiply by, right? If we're tripling, we actually multiply by 3, which is different than saying that we're increasing by 300%. Okay, sorry, we went a little over.